All right, so we're going to talk about intermolecular forces. First of all, we'll talk about some things. The first thing we're talking about is electronegativity. Now, electronegativity is just the ability of an atom to attract electrons to itself. So, in other words, it's just the attracting power of an atom, or how well an atom can attract electrons to itself. Now, we'll talk about polar atom or polar molecule. What's a polar atom or a polar molecule? Now, this is basically just an atom or molecule that contains an uneven distribution of charges. Let me give an instance. We can have hydrogen chloride, for instance. Hydrogen is bonded to chlorine. There's a covalent bond between the both of them. Yeah. According to what we said in the previous video, we said that covalent bond involves sharing of electrons. Let's try to draw the structure. Now, hydrogen has atomic number of 1. Chlorine has atomic number of 17. Sorry, not 17. Okay. Yeah, 17. Now, according to the shell configuration, this is going to contain 1 electron in the first shell. Chlorine is going to contain 2 in the first shell, 8 in the second shell, and 7 in the third shell. So the valence electrons are going to be 1 and 7. So according to the Lewis structure, as we said earlier on, hydrogen is going to have 1 electron outside, and chlorine is going to have 7. So we have 7. So I have 1, 2, 3, 4, 5, 6, 7. So they're going to, both of them are going to donate 1 electrons each, so that they can have a complete octet structure. So we're going to have hydrogen, chlorine. There's going to be sharing of electrons 1, 2, 3, 4, 5, 6, 7. Then the one from hydrogen is going to be here. So as we said last time, hydrogen now has a complete duplet structure because the first shell contains 2. Chlorine has a complete octet structure, which is 8. Now, obviously they shared the electrons equally among themselves, but due to the fact that chlorine is more electronegative than hydrogen, chlorine is going to tend to pull. We said electronegativity is the attracting power, how well an atom can draw electrons to itself. So since this chlorine has more electronegativity, it's going to pull most of the electrons to itself. You understand? So it's going to leave. Let me give you an instance. It's going to leave this bond. It's going to make the bond between them polar. So you have hydrogen and chlorine. Based on the fact that chlorine has more electronegativity, it's going to pull most of the electrons to itself. So it's going to have a partially negative symbol, and this is going to have a partially positive sign. Now, why it is partially negative is because it has pulled most of the electrons to itself, so it's electron rich. Now, the side that is electron deficient will have a partially positive sign. So now this is what we call a polar molecule. Understand? It is just basically an atom or a molecule. Is a molecule that has an uneven distribution of charges. Yeah, this is an uneven distribution of charges, and such that one end has a slightly positive charge and one end has a slightly negative charge. In other words, this can be called a dipole. This can be called a dipole. So this kind of molecule is called a dipole. It has two poles. It has the positive pole. This is the positive pole, positive pole and negative pole. That's why they call it a dipole. Now this is an example in terms of molecule. Let's look at an example in terms of an atom. So let's check. Okay, let's look at another example of a dipole. Now check the bond between hydrogen and oxygen, which gives water. So we have oxygen and we have hydrogen. Now, according to the periodic table, or according to by measuring it, oxygen is more electronegative than hydrogen. So in this bond, oxygen is going to try to pull most of the electrons to itself. So it's going to be electron rich. And as we said, the side with more electrons will be partially negative, and the side with less electron or electron deficient will be partially positive. So this is a polar molecule. That's why they say water is polar. So let's look at an example of a non-polar. Let's take chlorine molecule, Cl2, chlorine bonded to chlorine. Now in this kind of covalent bond, you can observe that both of them are similar atoms, so they share the same electronegativity. They have the same attracting power. So this kind of molecule is a non-polar molecule. It is a non-polar molecule. All right, so these examples here, okay, the above examples. This example, the one of hydrogen chloride, as well as water. These are example of permanent dipoles. They are permanent. They are permanent dipoles. Matter any molecule of water you have will always exhibit this dipole moment. Always exhibit this polarity. So we go to a case of an atom. Let's take an instance. We have an atom this way, and we have obviously the nucleus of an atom is positively charged due to the presence of protons, and the electrons roam around the nucleus. So let's say we have this atom. Now, this is a non-polar atom because obviously there's no imbalance in terms of the charges. Everything is well distributed. Now, but this non-polar atom can be polarized. Now, it can be polarized in the sense of, now we know that electrons are not they're not stagnant. They usually move around the nucleus. So as they move around, there's a tendency that at some certain points in their movement, the electrons might be packed towards a particular side, let's say the left hand side. during their uneven distribution around the nucleus. Let's say three of the electrons are now packed towards the side. This atom has been polarized. Understand? So in essence, this atom will have like it kind of we have like a kind of since this side is the electron deficient side, is going to have kind of a partially positive charge, and since this side is the electron rich side, it's going to have a partially negative side. So this has become a polar atom or a dipole. But this kind of polarity is it's a temporary polarity, because as the electrons keeps moving around the nucleus, they can easily come back to this configuration. So this is called a temporary dipole. So that's basically the difference between a permanent and a temporary dipole. So we're going to go straight to the types of intermolecular forces. So the first one we're going to discuss is the ion dipole forces. The first is the ion dipole forces. Now, this results when an ion, an ion, and a polar molecule are bonded or attracted to each other. Let's take an instance. We have the water molecule H2O. Now, according to what we established, we said oxygen is more electronegative than hydrogen, so it's going to pull most of the electrons to itself, and it's going to be electron rich. So it's going to carry a slightly negative charge, and hydrogen, which is now electron deficient, is going to carry a slightly positive charge. Now let's say there is a sodium ion trying to being dissolved in water. So say we have a sodium ion with a positive charge. Now there's going to definitely be a bond between sodium and oxygen, because sodium is positively charged and oxygen is slightly negatively charged due to its high electronegativity. So this kind of bond is the ion. This bond here is the ion dipole bond, or the force of attraction here is the ion dipole force. This is an ion and this is a dipole. That's why we call it an ion dipole bond or force of attraction. So we go to the next type of intermolecular force. The second type is the van der Waals forces. Van der Waals forces or bonds. Now, these van der Waals forces are just electrostatic forces. They're electrostatic forces between molecules. They're just forces of attraction between molecules with either permanent or temporary dipoles. So any force of attraction between, let's say, a dipole and a dipole, this can be permanent. They both can be permanent. One can be permanent and one can be temporary. Both can be temporary. This kind of the force of attraction between these two is known as the van der Waals forces. So there are various types of the van der Waals forces. There are various subcategories of the van der Waals forces. The first category is the is the London dispersion forces. The LDF. London dispersion forces, the LDFs. The second kind, or the second subcategory, is the dipole induced dipole forces. The third is the dipole forces. So these are basically the three subcategories of the van der Waals forces. Now let's look at each of them individually. Now the first one being the London dispersion forces. Okay, now if you have, let me use the context of, let me give you an example to explain the London dispersion forces, the LDFs. Now let's assume this to be a molecule, and let's assume we have this as a molecule. We have the, let's say we have the shared, let's just assume this to be, okay, let's assume this to be an atom, for instance, as we said earlier on. And we said the electrons roam around the atoms. And we said due to the arrangements of, or due to the random movements of these electrons, sometimes they are packed in an uneven distribution, or they are distributed unevenly, such that some can be packed most to the left and few to the right. So let's say due to the arrangement or due to the random movement, most of them are packed to the left. So let's say just one is here. Now this has become a dipole. This is non-polar initially, because there is no pole. There's no slightly charged sides. It's just evenly distributed. But this has become a dipole, so you're going to have kind of like a slightly negative side and a slightly positive side. Now, this has become a temporary dipole. Now, if you place another atom beside this temporary dipole, so the atom is non-polar, but due to the fact that you place this atom in the presence of this temporary dipole is going to make this particular atom to become polar. It's going to make this become an induced dipole. It's going to try, since here is slightly positive, it's going to draw most of this atom's electrons to the left hand side. So this is what's going to happen. This side now will have a slightly negative charge, and this other side will have a slightly positive charge. So this is an induced dipole, while this is a temporary dipole. So this just London dispersion forces is just, I just use the context of an atom to explain. But in the actual sense, just imagine this is a molecule, you understand? Because we are dealing with intermolecular forces, not intra. So let's assume this is a molecule, and this molecule is temporarily is a temporal dipole, and it's in presence of another molecule, which it has induced to become a dipole. Now the bond between these two dipoles, the bond between the both of them is the London dispersion forces. Yeah, so that's basically the London dispersion forces. It occurs between a temporary dipole and an induced dipole. Understand? So in terms of a molecule, you can have a molecule. You can assume this to be a molecule. Let's say a bond between two atoms. You can assume this to be a molecule. Assume this to be a molecule. Assume this to be a molecule. So it just occurs between a molecule which is a temporary dipole and a molecule which became a dipole as a result of the presence of this other dipole. So we talk about the next kind of the next subcategory of the van der Waals forces, which is the dipole dipole forces. Okay, I didn't give an example of this. Let's see. Okay, I'll give an example actually. Okay, the second one. This is not the second one. The second one is the dipole induced dipole forces. Now it's kind of similar to the London dispersion forces, but we'll see the difference. The only difference now is that it's between a permanent dipole and an induced dipole. Let's say, as we said, we have a permanent dipole here. Just like we said earlier, an example of a permanent dipole is hydrogen chloride bond, where we said that hydrogen is partially hydrogen chloride bond, where we say hydrogen is partially positively charged and chlorine is partially negatively charged. Sorry. So this is a permanent dipole. Now, if let's say hydrogen chloride is made to be in the presence of chlorine molecule. Now, we also established the fact that chlorine molecule is non-polar, right? So if hydrogen chloride is brought to the presence of chlorine molecule, it's going to induce this chlorine molecule to become polar, because of this. Let's assume we have this slightly negative charge is going to like try to draw this slightly negative charge is going to try to repel most of the electrons, you understand? So this side is now going to be slightly positive, and this other side is going to be slightly negative, you understand? Obviously, we said, remember, like charges repel, as I said. So assuming this chlorine molecule now, the electrons are evenly distributed, and remember that electrons are negatively charged. So if it's close to this partially negative side, it's going to repel. So most of them are going to be stacked up around this place, you understand? So this is a permanent dipole. This is a permanent dipole, and this is This is a permanent dipole, and this is an induced dipole. So we have a bond between these two. So this is a dipole induced dipole force of attraction, or a bond, you understand? So we go to the third kind of example. Go to the third example. The third example is the dipole dipole interaction, or force. The dipole dipole. This is when we have two what do we call it? Two permanent dipoles. So let's take an example of still using hydrogen chloride. Still using hydrogen chloride, or okay, let's still use hydrogen chloride. Hydrogen chloride. We know hydrogen is the deficient side, so it's going to have a slightly positive charge, and we know chlorine is the sufficient side, so it's going to have a slightly positive charge. Now we have another molecule of hydrogen chloride, also a permanent dipole. Hydrogen chloride, hydrogen chloride. So also this is going to be the slightly, sorry, made an error here. This is slightly negative, not positive. Now chlorine is also going to be slightly negative here, and hydrogen is going to be slightly positive here. So these are like permanent dipoles here. So there will be a force of attraction between chlorine and hydrogen. Obviously, they have different charges here, so there will be a force of attraction. Now, this force of attraction is the dipole-dipole interaction. This is a permanent, it occurs between a permanent dipole and another permanent dipole. So an example of this dipole-dipole interaction is, or a subcategory of this dipole-dipole interaction is the hydrogen bond. The hydrogen bonding, or hydrogen forces of attraction. Now the hydrogen bond is a very weak dipole-dipole interaction. It exists between hydrogen and either fluorine, oxygen, or nitrogen. So it exists between hydrogen and fluorine, oxygen, and nitrogen. So we'll take an example. Let's say you have hydrogen fluoride, similar to the example we just talked about earlier. So this hydrogen is going to be slightly positive, and fluorine is going to be slightly negative. Same thing if you have another molecule of hydrogen fluoride. Now hydrogen is going to be slightly positive, and fluorine is going to be still slightly negative. So this is an example of a dipole-dipole interaction, but it is a hydrogen bond because it's going to occur between hydrogen and fluorine. So this is the hydrogen bond. This is the H bond. This is the bond. This is the hydrogen bond. You had the bond between a molecule of hydrogen fluoride and another molecule. The bond exactly between fluorine and hydrogen. So this is an example. Another example is the bond in water. The bond in the water molecule. We have hydrogen. We have oxygen. Hydrogen. We have another water molecule. Let's say we have oxygen, hydrogen. Now the oxygen is going to be slightly negative because it is more electronegative than hydrogen. It's going to pull most of the electrons to itself. Now the hydrogen is going to be electron deficient, so it's going to be slightly positive, slightly positive, and slightly positive. And so there's going to exist a bond between oxygen and hydrogen, because this is negatively charged, this is positively charged. There's going to exist a bond. Now this bond is between hydrogen and oxygen. Remember we said FON. So when if it's between either fluorine, oxygen, or nitrogen, it is no longer a normal dipole-dipole interaction. It is a hydrogen bond. So this is the hydrogen bond. Now we are going to talk about some of the characteristics of this hydrogen bond. So the first characteristics of hydrogen bond is that it is a weak bond. Yes, it is very, very weak. Second is that hydrogen bond helps in the determination of the boiling point and melting point of organic compounds. So if the hydrogen bond is very, very weak, you can easily break down the molecule, you understand? And that's why you can easily determine the boiling point of various organic and inorganic compounds. Now, another thing to note is that the higher the electronegativity difference between the atom, the stronger the hydrogen bond. So if there is a much more electronegativity difference here, if there is much electronegativity difference between this and this, or between this and this, the hydrogen bond is going to be stronger. So these are like just the basic characteristics or properties of the hydrogen bond. Now we go to the general characteristics of the van der Waals forces. We said van der Waals forces is weaker as compared to the hydrogen bond. Yes, although we said van der Waals forces are like a hydrogen bonds are like a subcategory of van der Waals forces, but in terms of comparison, hydrogen bonds are stronger than van der Waals forces, other kinds of van der Waals forces in general. Secondly, it is weaker than the ionic and covalent bond. Yes, both the hydrogen bond, the dipole-dipole, they are all weaker than the ionic and covalent bonds. They are independent of temperature with exceptions to the dipole-dipole interaction. Yes, the van der Waals forces are independent on or of temperature. They have nothing to do with temperature, except this dipole-dipole interaction where you now consider both the hydrogen bond. That's why I said hydrogen bond helps to determine the melting and boiling points of organic and inorganic compounds, because it has to do with temperature. So this is the only exception. The only exception is the dipole-dipole interaction. Now they act over a very short range. Yeah, van der Waals forces act over a very short range. So this is basically just what you need to know. Now let's go over everything we said from start to finish. Now we started with we talked about electronegativity, the attracting power of an atom, or how well an atom can attract electrons to itself. We talked about polar and polar atoms and polar molecules. We said an atom becomes polar because of the difference in electronegativity. We took an example where we said hydrogen and chlorine, that chlorine would draw most of the electrons to itself because it is more electronegative than hydrogen. So the side that is electron sufficient, that has more electron, is going to carry the negative charge, while the side that is electron deficient is going to carry the positive side. And we call this a permanent dipole because for every molecule of hydrogen chloride, it's going to be this way. I will give another example in terms of water. We said water is also polar because oxygen is slightly negative. It's more electronegative than hydrogen, so it's going to pull more electrons to itself. Now we gave another example of a non-polar molecule, which is chlorine. Due to the fact that this is an atom of chlorine, this is an atom of chlorine that bonded together, they have the same electronegativity. There's not going to be any uneven distribution. The electrons are going to be distributed equally. Just like a tug of war, trying to do a tug of war, the stronger party will pull more electrons to itself. Now we talked about an atom. We said this is, let's say, a non-polar atom because the electrons are evenly distributed around the nucleus. We said this non-polar atom can be polarized, can become polar. That's what polarization means. Can make it polar. And how can it be polarized? We said it is polarized because of the movement of the electrons around the nucleus. Electrons don't stay they don't stay at a particular position. They are always moving. So there will come a point in time when the electrons will be some will be tightly packed at a side, and the others will be deficient. So the side that is packed with electrons or electron rich is going to be the slightly negatively charged side. So we call this a temporary dipole because the electrons can still move back to their original configuration. So this has become a temporary dipole. Understand? Now we talked about the various types of the intermolecular forces. We said the first is the ion dipole forces, which occurs between a permanent dipole and an ion. We gave water as an example of a permanent dipole. The next we talked about the van der Waals forces. We said it's just an electrostatic force between molecules of either permanent or temporary dipoles. So any force of attraction between the dipoles, whether permanent or whether temporary, is a van der Waals force. So we said van der Waals forces are subcategorized into the London dispersion forces, the dipole-induced dipole forces, and the dipole-dipole forces. So we talked about the London dispersion forces, where we said if you have, we assume this to be a molecule. Let's say we have this as a molecule, and there are even distributions of electron around the molecule. Based on the same thing we talked about, how a non-polar molecule can be polarized. So this became polarized, and we had a temporary dipole. Now, if this temporary dipole is placed in the presence of a non-polar, this temporary dipole is placed in the presence of a non-polar atom or a non-polar molecule. Due to the fact that this place is positively charged, most of the electrons are going to try to come to this side because obviously positive will attract negative. So this electron will try to shift towards this side. So you're going to have this place as being slightly negative because we said the side that is electron sufficient or electron rich is going to be negatively charged. So this has become an induced dipole, and it is induced because it is induced by this temporary dipole. Understand? So we talked about the dipole-induced dipole forces, which occurs between a permanent dipole and an induced dipole. The difference between the two is that this occurs between a temporary dipole and an induced dipole, while this occurs between a permanent dipole and an induced dipole. So this is the dipole-dipole force of attraction or bond. Now the next thing we talked about was the dipole-dipole interaction, where we have a bond between a permanent dipole and another permanent dipole. So this is the dipole-dipole interaction or bond. An example of, we said a subcategory again of a dipole-dipole interaction is the hydrogen bond, which occurs between hydrogen and FON, fluorine, oxygen, and nitrogen. We give an example. This is the H bond. Now, so there's something to note that this bond here is not the H bond. This bond here is the covalent bond, you understand? While this bond is the hydrogen bond. We give another example of a H bond in water, the hydrogen bond in water that occurs between oxygen and hydrogen. And we gave some characteristics of the hydrogen bond, and we gave some characteristics of the van der Waals forces. Yeah, thanks for watching.